Hello, my name's Ava Falsing, and I'm here to present our introduction, purpose, and vision of our senior design project. A UAV is an unmanned aerial vehicle, and a UGV is an unmanned ground vehicle. These vehicles are controlled via direct link from ground control station, or they can be completely autonomous. These vehicles are used to traverse terrain that may be unsafe for human travel, and are generally more efficient and faster at traveling. They can also use artificial intelligence or machine learning algorithms for mapping, image recognition, or targeting purposes. So, Raytheon Technologies is a defense and aerospace company that annually hosts the Unmanned Aircraft Systems, or UAS, University Innovation Showcase in order to encourage innovation in the UAS field and solve existing real-world problems. Multiple teams from different universities will develop, implement, and test hardware and software components to design the UAS to complete specified tasks. At UTA, we have a team of electrical engineers, mechanical engineers, and computer science engineers who work together to create both a UAV and a UGV platform in tandem for the competition. The UAV, or the Seeker, has to fly within field boundaries and identify UGVs by scanning a Roku marker on top of the ground drones. If the UAV scans its own UGV, it has to ignore it. If the UAV scans a faux UGV, it must tag it with an IR laser. Only one UAV must fly at a time. It can fly on any path. It has to find and scan the UGVs in any order, and the UAV has the full duration of the task to search and fire upon UGVs. If the UAV finishes early, it is able to try again. So for a task that's 10 minutes long, if the UAV flies in 3 minutes, it's able to try as many times as it likes to get the highest score within that 10-minute block of time. So, shown on the top there, that is our UAV that we used for competition, and on the bottom, that is our UGV that we used. So, the UAV is supposed to detect and fire at an enemy, and detect and ignore the friendly one. For the tasks, the evaders must complete predetermined paths at variable speeds alongside each other's schools of evaders. So task 1, we have allotted 10 minutes to complete this task. The evaders are placed at random positions in the field and cannot move. The only job the evader has in this task is to just transmit and detect and transmit when it gets hit. For task 2, all the evaders start at one side of the field and drive slowly across in a straight line at about 0.17 miles per hour. Again, this task is 10 minutes long. The the Seeker has 10 minutes to detect and shoot as many faux evaders as possible. For task 3, the allotted time is 7 minutes for this one because the evaders are going faster now at about 0.3 miles per hour. And again, they all start one side of the field, and at a certain time, depending on which lane they're in, the evader will take a 90-degree right turn, travel 2 feet, and make another 90-degree left turn, and finish the path. For task 4, it's a fast task at only 3 minutes long. The evaders are growing fast at about around 0.7 miles per hour. But for this task, the evaders will swap lanes with another evader. So it'll travel a certain distance, and after a certain amount of time, will make a 90-degree left turn or a 90-degree right turn, travel 24 yards, and then take another turn to finish the task in a straight path. It also is important to note that on the actual competition day, we did not do tasks 3 and 4 due to time constraints. We only performed tasks 1 and 2. So, for the Seeker, the UAV must be registered with the Federal Aviation Agency, and at least one team member must be an FAA certified drone pilot. So once we registered it, we got a certificate of registration and the license sticker that we pasted on the UAV's chassis. In addition to that, we also had an extra pilot get certified in case of an emergency, and shown here are these pilot licenses. For constraints, both the Seeker and Evader must be completely autonomous, and they must use the ACE combat system. The Seeker must use the ACE combat laser for firing at the foe evaders, and once it fires, it must also publish a software log saying that it attempted to shoot an evader at this time. For the evader, it has to have a receiver on it. Once it detects a hit, it publishes a log saying it got hit, sounds a buzzer, and lights LEDs to let judges know that it detected a hit. In addition, both drones must remain within the 50 by 50 yard field, and the Seeker must identify the invaders through the Aruko marker shown on the top.
Hello, I'm Carlos Mella-Rijo, and I will be going over our design and development for the UGV and the UAV. Now, our predecessors had quite a different showcase to perform for. They were only responsible for having a UAV that could detect Aruko markers and to have sensors for obstacle avoidance implemented. There were several design choices that were kept for our own UAV. Using the Raspberry Pi in Cube Orange was a good call. It allowed them to have fully autonomous navigation system with auxiliary functions performed by the Raspberry Pi. This is also something we use for the UGV. In fact, all the hardware and firmware in general was very efficient, so we use most of the same parts when constructing our UAV. However, there were also several shortcomings that we wanted to avoid for this next competition. The drone was unable to identify markers with the second task. To be safe, we upgraded the camera from a 2 megapixel camera to an 8 megapixel camera, which should allow us to see markers from further up and at higher speeds. The body became damaged during the third task. Our MAE team decided to overhaul the UAV body's design and to build it out of carbon fiber. Due to inclement weather, the competition was moved indoors. Once indoors, the drone could not arm because it required a GPS fix to be able to successfully take off. And indoors, GPS signal is generally unattainable. We also plan to implement indoor navigation by using an optical flow sensor and LiDAR to navigate without GPS. Okay, so here's our UAV's block diagram. First most important components that we have are the flight controller, which handles all the navigation and controls all the external sensors, and the companion computer, which handles all the processes that the flight controller can't, like our Python scripts for the IRC connection, internet connectivity, processing of the Aruko markers with the camera, and other smaller processes. These would both get power from a 8,000 milliamp hour lithium polymer battery that would then pass its power to be quote-unquote cleaned by the power module. So this should negate any spikes in power for whatever reason, say like a peripheral malfunctions or something along those lines. Then the other components would be powered through this power distribution board right here, so our Maytech Mini Power Hub. We selected this because it has battery elimination circuits that actually step down the voltage from the 14.8 volts that the battery gives to 5 volts for the companion computer and other peripherals. And then of course we have the actuators, which are the brushless DC motors, which get power and signal from the electronic speed controllers. Now the ESCs are powered separately from the PDB, but then they get their signal from the flight controller, and that facilitates motion. And here we have our UGV's block diagram. It's not that much different from the UAV's block diagram. We only have a single motor, and we also have an added servo here that the ESC controls. But beyond that, we have mostly the same components. We don't have any optical flow on here, instead we just have a 360-degree LiDAR right here. Our battery is also not 8,000 milliamp hour, it's 5,200 milliamp hour instead. It's a 2S instead of a 4S battery, because I don't think any of these components can actually handle anything above the 2S. Everything here is exactly the same. Now, originally started with an RC race car, the Traxxas Rustler XL5 here. We got rid of its default electronics, we changed the gear ratio so it would run slower, and we printed platforms for all the electronics and a Ruka marker for our version 1 design. After testing this design, we actually had it redesigned so that it could fit our peripherals better. It also had a dedicated mount and stand for the GPS. And of course, the final design also included a protective case that was fixed on with a strap. Now, our UAV's design wasn't built from a base, so we used a test room provided by the CSE department. Our UAV's prototype was inspired by last year's team's design, but it had several key differences. The drone is now much larger than before. This lowered the center of gravity so that while in motion it was more stable. The propellers were also fixed with propeller guards for safety. Now, these landing cushions, I believe they picked a different material and also had dedicated mounts for them so that they wouldn't break as easily. And these mounts also provided inserts for these trusses here that also provide more sturdiness and stability to the overall body design. Now, the final body design isn't really that much different. Safety wire was added because it turns out during landing these propeller guards would actually have upward motion and they would touch the propellers and actually get cut off. So this prevented that from happening. And the chassis had some minor adjustments so that all of the components could fit better. Now, an important part of our design here was the extended calm wind filter, or EKF, which we use to estimate vehicle position, velocity, and orientation. And that's based on our GPS data, our compass data from both the Pixhawk and the GPS, and accelerometer and gyroscope data from the Pixhawk's internal inertial measurement sensors, or IMEs. Now, this algorithm is already a part of Mission Planner, so all we really had to do was set everything up in the parameters so that I could use the GPS, and just make sure that KF is acceptable values. If values are, for example, too high or abnormal, Mission Planner has internal sensors that will monitor that. If you just click that EKF status icon, that's going to be in our home screen here. So just some tips and lessons learned for the body design and the electronics is something that might get better performance for the design is to increase the number of motors on the drone. Like, for example, a hexacopter, or if you really want to get crazy, an octocopter. You can actually go a lot faster with it, and you can be more stable. Make sure you design the body for the desired length of wires to reduce electromagnetic interference between components. That was actually a big thing that prevented us from using the GPS correctly during our testing and development phase. So once we reduced the interference by adjusting the wiring, the GPS fared a lot better. Now, another thing you can do is to twist the wires. This will cancel out emissions from equal to opposite wire signals, like 5V and ground for a peripheral, or RX and TX, for example. Another thing that might help is having retractable landing gear for the flight. Might give a better center of gravity and reduce drag. We fared well enough without it. It's just something that one of the competitors had. It's not a top priority. And of course, make sure your GPS module has RTK.
And now for our testing of the components, starting with the ACE Combat system. So our electronic speed controller goes to the ACE Combat to power it, which gives a signal output to the motor upon being hit with an IR signal. And upon being hit, a PWM signal is sent to the Raspberry Pi to send a message to the IRC server, which I'll show in a later slide. But it also flashes the LEDs, sounds a buzzer, and spins the motors, which we can see in this video. For autonomous navigation, we had to ensure that the GPS was also able to get a fix. So in the beginning, the GPS wasn't getting a fix at all, and if it did, it was a very low signal. We went through a couple of GPS modules, and upon elevating the component from the frame, we found a significant increase was found. And this is because of EMI, so especially from our power cables, once we elevated this, we obtained a decent signal and we were able to run missions autonomously. And in case the competition was held indoors, we also looked at implementing ROS, Robot Operating System, and SLAM, Simultaneous Localization and Mapping, to navigate without a GPS connection. This would have been done with the A2 LiDAR and the Raspberry Pi for processing, but ultimately the competition was held outdoors. The mission planner also includes PID tuning for waypoint missions. In the beginning, we tried tuning these parameters, but ultimately we left them near default once the GPS signal became better. And in the left video, we can see that we're in the quad, the engineering quad, which gave us pretty bad signal, but out in the field, we were able to run missions pretty well. And this is the LiDAR we would use for indoor navigation. We can see that we have obstacles that you can see in Mission Planner in the right image. This integrated a lot better with our Pixhawk flight controller, and it was also easy to use rather than the A1, which gave us a lot of hardware problems. And for competition, we had qual tests to score points before the competition to show that our drones could complete the given tasks and also change parameters on the fly. And these are some of the runs we did to complete those tasks. And for hardware, we learned to move power lines away from our GPS and label connections for orientation of our wires, and also organize the layout of the drone, more especially for component mounting and wires. And this is our IRC script working. So we connect to the IRC server, and once the Ace Combat knows it's been picked with an IR signal, the Raspberry Pi sends a message to the server along with the other universities during competition with a timestamp. This is just an example of what the IRC server code looks like. For software, adjustment of the servo trim saved a lot of time since PID tuning is a lot of trial and error. Also simulating tasks before field testing, and ensure that the waypoint radius is set big enough, otherwise the drone may overshoot the waypoints.
Hi, I'm Nick Partlow, and I'm here to talk about the team management for our engineering design project. Here we have the team structure and hierarchy, though some may be quite familiar. Here we have Carlos here as our project manager, as well he's also the team lead for the electrical engineering team. Here we also have Javier, who leads the DSE team, Vishnu, the ME. And up here we got our three advisors from A, and our two mentors from Raytheon. Next here is a breakdown of all of roles that each member of each team had to perform throughout the project. Got the electrical engineering team, who worked mostly on the ground drone, the mechanical team, who worked on the body designs for both drones, and the CSC team on setting up and programming for the air drone. And here you can see what each team member did. Complete those tasks. So, as for how we kept in touch with each other, one of the biggest things we did was use Microsoft Planner. There we would have assigned tasks each member of each team that would keep them up to date for their assigned tasks and send reminders to mark each task as complete prior to due date. And can't have a project without some Gantt charts, of course. We also did we also used Microsoft Teams and SharePoint to also for some conferences especially on Fridays, where we talk to our sponsors about how progress is. And of course, we'd also use the GroupMe app for maintain casual conversation between groups in case there's like something urgent that we discuss. And of course, I just mentioned earlier about the weekly meeting for discussing our project. And lastly, we mostly used our class time on the project, but there were times in case we were unable to complete certain tasks that we need outside of class time. Here is the budget for all the parts we bought for this whole project. Most of them were parts that were also used by the UAV for previous year. Though there have been some changes were also made to ensure that we would not make this. One of which was that we got ourselves a higher quality camera for the UAV, as well as optical flow sensors for autonomous navigation without the use of the directional LiDAR to help with the optical flow, and some carbon fiber frames for a stronger body that can withstand more stress. And of course, here's the parts that we got for the UGV. Here, fortunately, we did not have to. We were able to remain within our budget, and we did not have any need to replace many of the parts that we were able to keep. We still had some remaining funds left. So the lessons that were learned one, for example, is that we had to maintain and this is an advice for future, that would be necessary to have more input than online. Like, some of the apps we did were good, maintain contact were good, but I feel as though it would have helped build a better connection with other teams person. Because aside from the teachers, most and all the other groups didn't really have much contact with. And of course, there was also the matter of schedules and division of labor. Like, a part of the reason why some of the other teams touch with each other was that there was like everyone had their own schedule, and it kind of like prevented us from actually having more in-person meetings. I mean, I get it's understandable if people have their own time, but it would be nice to be flexible. And that leads to better utilize each person's skills when having better communication. That way we can prevent any misunderstandings, and if we're having trouble, we can always ask other groups how to approach it.
Section 5. Results and Conclusions. For Task 1, our UGV IRC chat script was constantly triggered by the sun. However, everyone had this problem, and there was no real fix that we could do in real time because infrared receiver was required by Raytheon. Eventually, we just turned it off on the UGV and we relied on the logs sent from the UAV to determine if a UGV was hit. From the UAV's perspective, it managed to record and hit all 3 enemy UGVs and ignore the friendly UGV. However, at the end of our run, the UAV fell out of the sky, and there's several theories we have for it. The first one is that the center of gravity of the drone didn't warrant hovering very well. Another possibility was that the Raspberry Pi became unplugged right at the end, causing it to crash. Additional problems came with the hotspot. We needed the hotspot to connect to the UAV as well as the UGV. However, range became a problem as the UAV was flying around. Later, we used 2 different hotspots, and we followed the UAV around in the field to ensure that it stayed connected. For task 2, our UGV initially got off to a rough start. It had trouble mounting, as well as it would continually veer off and not stay in line. After resetting it, however, we managed to stay online and drive down the path at the desired speed of 0.17 miles per hour, and we reached the other side. The UAV managed to identify 2 out of 3 enemy drones and ignored the friendly drone. We missed the third one because one of the other competitors' UGVs sped across the field much faster than anticipated, so by the time our UAV reached that section of the field where the other drone was, it was no longer there. It was on the other side of the field. In the end, we ultimately won first place, second place went to UT Austin, and third place went to UT El Paso, and the rest were honorable mentioned, not ranked in any particular order. The main thing that set us apart was our qualification testing that we did prior to the event. We racked up a lot of bonus points for doing this, and it really pushed us ahead. Additionally, we started testing right when we could, as soon as both the UGV and UAV were ready to fly and register hits. And we used easy, friendly parts which could be swapped out whenever something went wrong, which greatly reduced time of having to fix any particular problem we ran into. And that concludes our presentation of our senior design project. Thank you for watching.